Okay, you're all set.
Okay. So hello everyone. I hope the practical work yesterday was okay. So this morning we still have some more theoretical sessions, and so today we will start with some a kind of a short review of some studies using Worms PISCES or CROCO PISCES. So I will start presenting some of these studies, and then Odette will present also some studies, and then we will carry on. Okay, so I will show many free examples. Since I worked a lot on the Peruvian cooling system, I will mention different studies. One on the long-term trends over more than 3 decades in the Peruvian oxygen minimum zone. I've worked a lot also on climate change, so I will present some work we did fairly recently using the CMIP 5 scenarios, worst case scenario, and its impact on the Peru cooling system. And I will show briefly a study on the impact of sub-mesoscale dynamics in an upwelling system in the Peru cooling system. Okay, so first a few words about the CROCO model configuration that we use in these studies. So it has already been explained a little bit yesterday. So the model needs some boundary conditions. So we use different models for these boundary conditions. Generally, they are global models, and they can have various spatial resolution. For instance, it can be 1/12 of a degree with a Mercator model, which is a French global model. It can also be in 1/4 of a degree, and even for climate studies, generally it's around 2 degrees. So 2 degrees is a kind of a lowest resolution we have used for our studies. But of course, it depends on the grid that you use for your model. So in our case, the grids are around 10, 20 kilometers. In this present case, it's 12 kilometers for this Peru grid that you can see on the right side. And also for biogeochemistry, we need boundary conditions and initial conditions. And these unfortunately, there are no models that, to my knowledge, that are presently realistic enough to provide correct initial and boundary conditions. So what we use generally are climatologies that you used yesterday for the practical session. So these climatologies, they can be, they are named CARS or World Ocean Atlas, or also GLODAP for some of the biogeochemical fields. And for iron, as I told you, there are no climatologies, so we use data from a global model. Now, this poses some problems when you use climatologies, because generally you don't use climatologies for the physical conditions. So there is some kind of inconsistency between the physics and the biogeochemistry at the boundaries. In some cases, it can be a problem, I guess. For Peru dynamics, it's not really a problem because the forcing in the equatorial region is very strong, and it can modify it's strong enough to modify correctly the biogeochemistry inside of the domain. Okay, so before we go into these examples, what I want to stress is that when you're going to do a biogeochemical study, it's very, very important to look at the physics first, because the physics, as I stressed yesterday, is very important for the solution. So you need to evaluate the physics is using whatever kind of data you have. It can be sea level from satellite or from some coastal stations, temperature, currents, mixed layer depths. It's very important, and the realism of the biogeochemical fields will really depend from the realism of the physics. So in this example, we used for the Peru system, we used the sea level. So this is a this time plot between 2013 and 2017 displays the sea level in a coastal section of Peru around here, and average in this box. And what you can see in red is the observations, and in black is the model. So there is a good correlation between the two signals, and it's very important in this system because it shows that the model is able to represent the propagation of coastal trough waves, which is a very strong signal in the Peru system. The coastal trough waves propagate eastward, or the equatorial waves propagate eastward and then trigger coastal trough waves that propagate southward. It's also important when you have the opportunity to try to evaluate the model, the mean flow of your model. So in Peru, there was a paper done with some ADCP observations, 5 years of ADCP observations, also averaged over several sections. And here we have the well-known alongshore poleward current, which has a maximum velocity of around 9 centimeters. And when we take the RAMS model, in this case, for more or less the same period, we have a relatively good agreement with a maximum velocity of 8 centimeters per second. You can already note some differences with the topography. The topography is not the same as in the observations, and this is due to the fact that there is a necessary smoothing of topography when you use sigma coordinate models. Okay, so now when you have evaluated your physics and you are satisfied enough, you can begin to evaluate the biogeochemistry. And one very powerful source of information is to use satellite data, chlorophyll satellite data. In this case, it's a climatology over the years 2013-2016 from the MODIS sensor. And what you can see here over Peru is a high concentration of chlorophyll near the coast due to the upwelling dynamics that bring a lot of nutrients to the surface. And then this concentration decreases offshore because there is all the nutrients get consumed, etc. So you have really this characteristic cross-shore gradient of chlorophyll, okay? And then when you look in the model, well, you represent also this cross-shore gradient, but the model has a bias with too high concentration of chlorophyll. So depending on what you aim to do with the model, it can be a problem, or maybe it's not really a problem. If you're doing a process study, if you want to understand how the system works, how it reacts to different forcings, or if you change parameterization, you want to see the reaction of your model, maybe it's not a problem to have a relatively important bias. But if you want to do something really realistic, then it means that you have to tune your model, try to adjust some parameters to reduce this high chlorophyll. Okay, and if you look also, okay, this was the mean chlorophyll, but one very important thing also is to try to evaluate the seasonal cycle. So what we did here is to average the chlorophyll in this coastal box here in black and plot the evolution over time with one data point every month. So it's a monthly time series, and the variations are between 1.4 and almost 4 milligrams of chlorophyll per cubic meters in the data. And you can see that in the observations, we reproduce relatively well the seasonal cycle, but we have too high chlorophyll values. I say relatively well, but you can see that there is also another problem with the model with a too low concentration in January in this simulation, which is not present in the data. Okay, so this is the kind of validation that you can do with satellite data. What's really interesting, and I want to show an example here, is to use also in situ data and, for instance, glider data. So here, what we did is a glider campaign of Peru. Here you can see the section. It's in the northern part of Peru. And this is the section, a zoom on the section. And what the glider did is several travels offshore and then came back near shore, etc. 3 times. And what is plotted here is the current, the depth average current over the glider, the depth that is investigated by the glider. And you can see this strong poleward current due to the arrival of El Niño here in blue. Okay, so this is the period. Sorry, I didn't mention the period. So what we did is to put a glider in the water in November, December 2015, at the beginning of the 2015-2016 El Niño. And what you can see here is the temperature measured by the glider. So here you are near the coast, here you are offshore, then you come back near the coast, then offshore, then again near the coast. And you can see that at the end of the period, so near the 10th of December, you have a strong warming of the surface layer, which corresponds to the advection of warm water due to El Niño. Okay. Then if you look at the model, which has, in this case, a 4-kilometer resolution, it's not exactly the same model as shown before, is able also to represent correctly this warming. Okay, the glider was able also to measure oxygen, and it's a very important parameter in this region. So here you can see the vertical structure of oxygen with the high oxygenated water near the surface and low oxygenated water near the bottom, with very low oxygen around nearly zero near 200 meters. And what you can see is that near shore, this ellipse shows what happens near shore. You have very low oxygen near shore, and then about 2 weeks later, you have highly oxygenated water, which means that these warm waters that are advected towards the coast are also oxygenated deep waters that can reach relatively high depths, around 100 meters. And the model, to some extent, is able to represent this oxygenated water, this advection of oxygenated water near the coast. So evaluation of your model is really important for the physics and for the biogeochemistry. Now I'm going to talk about one study about the trends of oxygen variation in the Peru cooling system. So there were 2 papers done on this study with Dante Espinosa Moriberon, one about El Niño and one about the longer trends. I'm going to talk mainly about the longer trends. So what was the model configuration of this study? We used the PISCES model for the Peru and North Chile region. So the resolution was a bit lower, 20 kilometers, but we modeled, it allowed us to model a long period of 50 years. This kind of model can be kind of costly. So with a relatively low resolution, like 20 kilometers, which is already quite good for cooling systems, at least for the Peru cooling system, it was not too costly. At the boundary conditions, we used an American model which is called SODA, which has been used for many studies. It's a model that uses data assimilation, so it's relatively realistic in this region. And as I said, we used the CARS climatology for nutrients and oxygen. Then for the wind, we did different tests with different forcings from NCEP, from CFSR. We looked at the influence of various wind forces. Okay, so what is the context? In fact, when you look at SST measurements from satellite over the period 1994-2014, and if you look at the trend of SST, so the slow evolution of SST, what you can see is that in the south of Peru, you have a strong cooling of SST, and also in the north of Chile. And this agrees if you take some in situ chlorophyll measurements in this region, in the Pisco region, you have an increase of the chlorophyll. So a cooling could be related to an increase of upwelling, and this cooling, this increase of upwelling could also bring more nutrients to the surface, and so explain the surface chlorophyll trend. And if you look at oxygen, you have a bit slightly the same story, but with slightly different variations. So now we are looking at, in this plot, we are looking at the oxycline, which is the depth, the surface that separates the highly oxygenated surface waters with the low oxygenated deep waters. So for instance, it's the 22 micromole here, which corresponds roughly to 90, sorry, there's a mistake here, the unit is wrong, I think. But okay, so what we can see is that the oxycline here is shoaling, so it gets closer and closer to the surface. And so the question was, we have consistent trends of temperature, oxycline, and chlorophyll, and what is the forcing of these trends? Okay, so first, what we did is, of course, evaluate the model realism. So with the IMARPE Institute, which is a Peruvian Sea Institute, a lot of data have been collected over a long period, over more than 50 years now. So there's a lot of oxygen measurements. And here is the depth of the oxycline, 22 micromoles. And you can see that we have a shallow oxycline near the coast, which is due to the upwelling, and deeper oxycline offshore. And if you look at the climatology, CARS climatology, which is a gridded climatology of the data, at half of a degree, you can really see this signal with the shallow oxycline near the coast. And the model, of course, is able to represent this shallow oxycline near the coast. So we have trust in at least in the mean state. Now, if we look at the evolution in time, so what we did is take all the data in this box, average it, and compute the mean oxycline in the box. So this is the blue curve over time, so since 1960 to 2008. And we did the same with the model. And we can see that there is a fairly good correlation. The gray bars correspond to El Nino events. And you can see that during the strong El Nino events, for instance, the one in 92-93, which was very strong, we have a strong deepening of the oxycline. So really the water column gets very oxygenated during El Nino, which is quite common, quite well known. And it also occurs for the north of Chile. Okay, so now we begin to look at trends, meaning that when we have a time series, we fit a linear trend in this time series. And if we look at the trends at different depths, so we have different time series at different depths. In red, you have the time series of the data. And in black, you have the time series of the model. If you look at the values, so we have a maximum negative trend of 10 micromoles per decade. It means that in 10 years, you lose 10 micromoles at around 50 meter depth. So this is quite important over time. So there is a trend towards deoxygenation. So the system is losing oxygen over this period. What is quite nice is that the model is able to represent relatively correctly this trend with the same shape. It slightly, though, overestimates the observed trends. You can see that the black values are too strong below 50 meter depth. So that's a good thing for the model. And also what we did is to try to see if we use the same sampling as the data, what kind of trend do we obtain? So this is the blue time series here is that we took the model values, but we sampled them exactly the same way as it was done with the ships of IMARPE during all this period. And what we obtain, so this is for the oxycline trend in this case, what we obtain is a much stronger trend than the model trend. So what this tells us is that the subsampling may impact the results, and that the model is probably slightly overestimating the trends. And the observed trends that we have here in red could be slightly weaker than the ones that we have calculated. Okay, so now what are the sources of variability in the system? Are they equatorial currents, or is it the wind stress? So what we did is we modified the boundary forcing and the wind forcing in our experiment. This is the idea of having a model, and you can play with it and you can test different physical forcings. So the main boundary forcing here is due to this zonal currents that are near equatorial currents, the equatorial undercurrent, and then these subsurface jets, the primary subsurface current and the secondary subsurface current. So these currents tend to transport water towards the Peru region, and they transport oxygenated water towards the Peru low oxygenated water. Okay, so we did several experiments with different climatological wind forcing. What does it mean? Is that first, we completely suppressed the wind forcing variations. So the wind forcing is a constant regular cycle over the 30 years, but we keep the internal boundary conditions. And we tested several wind forcings. So these are these different colored lines, and you can see that the Oxycline trend remains roughly the same. So the main forcing that is driving the Oxycline trend is the boundary forcing, is the equatorial dynamics. And if we suppress the equatorial dynamics variability, so if we take now a seasonal, regular seasonal flux for the EUC and primary jets, etc., then we completely lose the Oxycline shoaling. So we don't represent this deoxygenation. So this experiment shows that it's really the Oxycline that is the main driver of the deoxygenation in this region. Okay, so that was my first example. So the second example is a study of the impact of climate change on the Peruvian upwelling system. So I think you have all heard about these climate change scenarios. For instance, here is a plot representing the various radiative forcing of the different scenarios. So these are the CEMIC 5 climate scenarios, and you have the scenarios with mitigation, the scenarios with different types of economical scenarios as well. And here in gray, you have the worst case scenario with a steady increase of the radiative forcing. So these scenarios are studied with global, large-scale ocean atmosphere, and sometimes BGC, meaning biogeochemical models. And these models have a low resolution, so it's kind of difficult to see what happens in some local systems, such as the Peruvian upwelling system. If you look, for instance, at the bias, the error done in these climate models, this is an example. So here we took the climate model, which is IPSL CM5, which has 2-degree resolution in the ocean. And when we look at the mean SST, we obtain this. And you can see that near the coast, there is not, the signature of the upwelling is completely absent. If you compare with Pathfinder data, for instance, you can clearly see this cold water band near the coast. Here it's completely absent. So it means that there is no or very weak coastal upwelling in global models. So it's probably necessary to use the regional models like CROCO or ROMS to downscale climate signals. Okay. So what we did is to choose 3 different models which had a biogeochemical component, the CNRM model, which is a French model, which uses also PISCES, but at global scale, The GFDL model, which is a US model, but it doesn't use PISCES, it uses another model. An IPSL model, it's a French model that uses PISCES. And we chose these three models because they represented quite well the biogeochemistry in the region. And now, what we use is a ROMS PISCES model for Peru at 10 kilometer resolution. And which scenario did we choose? Well, we had no time to do all scenarios, so we choose the most pessimistic scenario, like RCP 8.5, which is the worst case scenario in terms of radiative forcing. Okay, so now first, if we look at the physical forcing, the wind stress in these scenarios, and if we average over the coastal area in the Peru region, we have an alongshore wind stress that is quasi not varying for the GFDL model, and that decreases for two models, the IPSL and GFDL model. It means that the upwelling forcing is going to weaken for 2 out of 3 models. If we look now, if we really compute now using ROMS, we compute the vertical velocity and the upwelling in the coastal box. What we see is that it's really different from the wind, and there is much more variability, a strong decadal variability. But we obtain for GFDL in blue a rather steady upwelling. However, for the two other models that have a wind decrease, the upwelling is decreasing a lot. It's a decrease of around 25% in 100 years. So yes, I forgot to say that with this model, we were able to simulate 100 years of scenario. So the upwelling is going to decrease very much for 2 models out of 5, out of 3. If we look at the SST, I'm not talking about biogeochemistry yet. I'm mainly focusing on the physics. You can see that the 2 models that have a decreased upwelling, in red and black, have a very strong increase of temperature. So we have an increase of 3 to 4 degrees in the coastal box. But also, if you look at the blue curve that had no change in wind and that had a steady upwelling, you can see that the temperature also increases by at least 2 degrees. So there is, even in upwelling regions which upwell deep water, you will have some warming due to the fact that it's not only the surface water that is warmed by climate change, but also the subsurface water. To give you an idea, the water depths that are upwelled in this system are around between 50 and 200 meter depth. So they are not very deep water, and they can be warmed by climate change. Now we're moving to biogeochemistry. So if you look first at the left side, the left figure, you have the nitrate line depths in global models. So you see that they have very different evolutions. One, the GFDL model is still very, very steady. Then IPSL and CNRM have very strong changes. What is interesting to see here is not only the trend, but also the mismatch, the error that is done in these models. For instance, if you look at the data available in the Peru region, you can see that the nitrate line depth is more around 20 meters, and that in these models, it's around 60 to 100 meters. So the error is huge, and that's why we need also to use these regional models, like ROMS. So when we use ROMS, PISCES, we are able to correct this bias relatively well. We still have relatively similar trends, but the range of the variations, or at least the initial values here, are in much more closer agreement with the observations. If we look now at surface chlorophyll, we can also see that these global models here have very strong bias and very different values, okay? So you can see the range. I mean, the CNRM model has mean values near the coast of less than or around 0.1 milligrams, while the GFDL is more around 0.7. So there is several orders of magnitude, almost one order of magnitude of error between the different models. What you can see is that all these models show a trend. Surface chlorophyll has a decreases for the three models. However, when you use the ROMS model, which is forced by these global models for surface chlorophyll, first, what you can see is that we are much closer to the observations. So here in this band, this green band displays the range of error that you have between different satellites. It means that the realistic values are around 3 and 4 milligrams. And then our data is around 4 and 6. So we are much closer, very much closer to the observations than the global models. This is the first thing. Then what you can see is that the trends are quite different than the trends that are obtained in the global models. For instance, one model doesn't change anything in its surface chlorophyll, the CNRM, but two models, GFDL and IPSL, they tend to slightly increase the surface chlorophyll. So this is interesting. This was kind of unexpected, also because, as you can see on top, for GFDL and for IPSL at least, you have a decrease of the nitrate line depth. So the nitrate line depth is getting deeper. However, you still have an increase of the surface chlorophyll. And if we look at the vertical structure of what happens, we have another surprise, is that the trends are really different if you look at the very surface and just below. And what is interesting is that it is a common vertical structure for the three models, is that we have an increase near the surface and a decrease in the subsurface. These are cross-shore sections with here the coast and offshore, 200 kilometers offshore here. And what we can say to explain this is that we have less nutrients. For instance, in the IPSL model, we have less nutrients upwell to the surface. However, because the wind is weaker, there is less also offshore transport of the phytoplankton. So there is probably more retention near the coast, which tends to maintain a relatively high concentration of phytoplankton. Also, there is more stratification and a shallower mixed layer. So there is a stable phytoplankton concentration at the surface and a reduction of phytoplankton below. Okay, so I'm getting to the last part, which is the impact of small-scale sub-mesoscale dynamics in the Peru upwelling system. Okay, so we worked with, this work has been done in collaboration with some German colleagues, Søren Thompson and Jard Hauschild. What we did with Jard is this kind of configuration with the same Peru grid at 1/9 of a degree, so around 12 kilometers. And we did an offline zoom, so we didn't use AGRIF, at 2.6 kilometers in this region of the south of Peru. We did this because there was a cruise done by the German colleagues with a lot of data in this region. Okay, so if we let's talk a little bit about subduction. So there is a lot of subduction in upwelling systems. To explain this, I drew this simple schematic, so with a classical view of an upwelling. So here you have the shelf and the coast, and here you have the surface winds that is blowing northward. So we are in the Peru upwelling. The wind is blowing northward, parallel to the coast. And the upwelling, or what we know classically from the upwelling, is that there is water coming towards the shore, then going to the surface layer, and then transported offshore by the Ekman current, which is labeled V-Ek here. But what happens if we have a thermal front, which is the reality? If we have a thermal front, it means that here we have cold water, and here we have warm water. So what happens at the front? Are the fluxes able to transform the water from cold to warm water? Sometimes yes, but sometimes no. I mean, there's not enough heating from the atmosphere to transform this water and to let it flow like this. So what happens is that you have subduction. In fact, the water comes to the surface, is advected, and then when it encounters a front with warm water on the other side of the front, there is subduction on this side of the front. And because there is also wind on the other side, so you will have some upwelling on the other side of the front, etc. So you have these kind of cells that are produced in the upwelling system. This is also a simplified view. It all happens in 3D. But what I want to say is that a lot of the upwelled water that is showed here, the upwelled water near the coast, is in fact subducted again slightly offshore. And this happens generally in filaments. So here we have an example on the observations. This is SST in 2013, and here in gray, what is shown is a glider section. So a German glider was deployed and repeated several sections here. And in one of these sections, you can see for the oxygen, for instance, so this is near shore here, and this is offshore, you have subduction of high oxygen. So this high oxygen has been produced due to phytoplankton, and it's subducted at around 20-30 meter depth. And what you can see that you can see also some high chlorophyll values here that can be explained partly by subduction. Okay, so what we did is use a model, the model that I just described. And what is sometimes really interesting to follow the water masses is to use ROMS offline tool. So this ROMS offline tool is a Lagrangian tool in which you can put particles which represent the water mass, a lot of particles, and you can run the model, this Lagrangian model offline, and follow the trajectory and characteristics of these particles. So what Yard did is to put a lot of particles in the cold water that are just upwelled here. So all these black dots, and then we follow them when they are subducted. So in this simple schematic, the blue dashed line represents the mixed layer. So we identify the particles as upwelled when they go upward and they cross the mixed layer, and they are subducted when they leave the mixed layer. Okay, so here, this is the time evolution of the particles, and the time 0 corresponds to the time when they cross the mixed layer. In red, you have the particles that are not subducted, so they stay in the mixed layer. And in blue, you have the particles that are subducted. So this is here, what is shown here is a depth. So here you can see that the particles that are not subducted are first around 40 meter depth. They cross the mixed layer, and then they stay at around 20 meter depth. Okay. And the particles that are subducted, they are slightly deeper, and then they they rise to the surface, but they begin to decrease their depth again in blue. What we could do with this here on the left side, you have an example of the parcel trajectories, and here we follow their temperature in color. So you can see that some particles here are in dark blue, and they are upwelled, and their trajectories become in yellow, etc. So it means that these particles, they stay in the surface layer. And some other particles, for instance, this one here, they are upwelled, and then they keep this very dark color, meaning that temperature stays really cold, so they are subducted again. Now, if we look at the nitrate concentration of these particles, for instance, here in red, this is the nitrate concentration of the particles that are not subducted. So if they are not subducted, it means that they stay in the surface layer where there is light. If there is light and nitrate, phytoplankton is able to grow, so nitrate is consumed. This is why we have a decrease of nitrate between 20, and the mean is 20, and it goes to around 12 micromoles. On the other hand, if you look at the subducted particles, the nitrate concentration remains more or less constant. This is because when they are subducted, they reach relatively deep depths that are below the euphotic layer, and so they are not consumed anymore by the primary production. Okay, and with this methodology, we were able to show that 43% of the upwell floats are subducted. So it means that almost half of the water mass is subducted again, which is huge. It means that when you have an upwelling, in fact, all this water, almost half of the water does not stay near the surface, but goes back to the deep layers. So that's one first information. And if we compute the nitrate concentration, we use the nitrate concentration of the floats, we were able to show that 40% of the upwell nitrate, so if you have an upward flux of nitrate in the surface layer, 40% of it will get subducted again. So this is this submesoscale variability through filaments is very important to put back some nutrients in the deep layers. Okay, and this is the end of my presentation. What time is it now? Yes, it's been 45 minutes, so I don't know if you have any questions. I could answer them.
Can I make a question?
Yes, sure.
You showed the glider measurements, but the glider spent several days in making that measurements. Is that delay? Can that delay affect the comparison with the model? Because the model, I suppose, the model is the section you showed of the model is 1 day or is an average.
Yes. Yes, you're right. In theory, it would be interesting to sample the model exactly the same way as the glider. This is kind of technical. I don't think there is a tool to do that in CROCO. One way could be to make outputs, because it's relatively short period, the glider. It's not for years, it's for less than 1 month. So, no, sorry, around 1 month. So for 1 month, you could output maybe the data every hour, and then really compare with the glider data. When I look at the results showing obtained with daily average from the model, I think it's already fairly good, and I don't think the problem comes from the sampling. I think the problems probably comes from for instance, the boundary conditions for oxygen, which were not very good in the case that I presented.
Okay, and I have another question. Do you use just surface data for the forcing of the model? Data of the just on the surface of the ocean and one layer of the atmosphere, or you can add more layers on the ocean for the forcing?
Okay. For the forcing, really, the forcing is applied. I mean, you mean the physical or the biological forcing? I mean, both are applied really to the first layer of the model. If you imagine wind stress is felt by the first layer, and then the mixing of the turbulence will propagate this momentum in the water column. But the wind stress, the impact of wind stress is really on the surface. For the heat fluxes, it's a bit different because, as you know, the solar flux penetrates. So the solar flux is the only forcing that warms the water column, not only in the surface layer, but also at greater depths. So for instance, if you have no chlorophyll, you can warm the till 100 meters. So, but besides that, all the forcings, atmospheric forcings, act on the first layer of the model.
Thank you.
You're welcome. I see there is maybe a question in the chat. Okay, they say, do you in the first study, do you know why the subsampling increasing the trend so much? No, I don't know. It's a good question. It's a good question. I mean, I think it's kind of interesting to do this test because you know that you do an error when you subsample with ships. So when you have a model, you are able to quantify this. But why there was an overestimate trend, I don't know. We didn't try with different ways to subsample. We really took the subsampling of the cruises. So I guess we would have to dig this more to answer it, to answer your question. There is maybe another question in the chat. In the future scenarios, you have increased chlorophyll in the surface and decreased in the subsurface. What is the trend integrated on the vertical? I think it's in my paper. I think the trend in the vertical is slightly negative. So, as you saw, the trends in the global models are negative in the surface. What we see in our model is that at the surface, it is slightly positive for two models, but it is negative just below. So if we integrate over the euphotic layer, I think we had slightly negative trends. So this, in fact, this is a bit consistent with what happens in the global model. It's not so different. I mean, in terms of sign of the trend, I'm not talking about the amplitude of the trend, but the sign of the trend. So it means that there is less phytoplankton as a whole in the system, which is probably a problem. Okay, but I think what is important also is that if the trend is different at the surface than below, it means that using satellites, you might have the wrong idea by looking at surface chlorophyll. For instance, imagine if in the 20 years we have satellite data over upwelling regions, and we look at chlorophyll and we say, okay, it's slightly increasing, so there is no problem for the ecosystem. Well, it might be, in fact, we might be misleaded because just below, in the subsurface layer, there is probably less chlorophyll. Yeah, and so Vera says the integrated trend is also consistent with less upwelling too. Yes. Any other question? Sorry, I need to plug my laptop. Yes. Okay. So I leave the floor to Odette, or we make a short break? Odette, what do you think?
Short break. Or,
Short break? Yes.
yes, 5
5
minutes
minutes?
or yeah.
Yeah. Okay. See you in 5 minutes.
Okay.